Hi, everybody. Can you believe that we're in Module 4 already? I sure can. So welcome to the asynchronous lecture. We'll just talk a little bit about forces. So note that there is no separate lecture for Module 4.1 and 4.2, as in the asynchronous lecture. There will be two synchronous lectures, but this is all you will have to watch asynchronously for Module 4, okay? So let's get started. Okay, so first, again, I know a lot of this is going to be a review, and you probably know of forces or can conceive of what a force is. But just as a definition, a force is either a push or a pull. That could look like a lot of different things. It acts on an object, right? Forces don't exist, independently of an object, right? They're not just out there somewhere, right? They have to be applied to something and act on something. It requires an agent, so something has to be doing the applying, right? Something needs to act on the object in order to apply the force. Finally, we know that since acceleration is a vector, force is also a vector. So we're going to be treating force as a vector from here on out. Okay, so I alluded to this before when we were talking about acceleration, but the reason that objects accelerate is that they are under the influence of forces. So if there's no force acting, the object is not going to accelerate. So note that that could mean a couple of things, right? It could mean that the object is staying still, so it's not moving at all, or it could be moving at a constant speed. So in order to change the speed of something, you need an applied force. So first of all, we will start with the first couple of Newton's laws. There's three, obviously, as you may know, but we are only going to look at the first two in Module 4, and then after the midterm in Module 5, we'll look at Newton's third law. So we kind of know Newton's first laws. It's one of those things that roll off our tongue when we're asked for famous physics theorems, right? Every object remains at rest unless it's acted on by a force, or an object in motion will stay in motion unless acted on by a force. So that's obviously, kind of foundational to a lot of physics, right? It's compelled to change the state by forces impressed on it. So I threw a few comics in there because there's a lot of people that joke about Newton and the first law. So take some time and look at the cartoons because I like them. I think they're funny. Okay, Newton's second law, another thing that we can just kind of rattle off, F equals ma. Of course, we are in our enlightened state that we know that force is a vector. So a vector will be used as well as the vector for forces. Here I have it solved for A, right? So obviously you usually do see it as F equals ma, but writing in this form indicates that the acceleration is the force, the net force divided by the mass. So it's force per mass, which is not often a way that acceleration is thought about as a force per mass, but that's what it is. When we see F net, what does that mean? I mean, it means that it's the net force, which is equal to the sum of all the forces. Okay, so obviously when you do that sum, you need to take in the direction. Okay, that's going to matter a lot to determine the net force. So yeah, what forces are acting on the object in total, and what is the sum of them, so the net force. So note that a unit for force you already know is the Newton, right? It's a kilogram meters per second squared, which we can get pretty easily from Newton's second law. So kilogram, it's written in SI units, but we will typically use the unit Newton. Okay, so important, and this might feel like an obvious thing based on the equation for Newton's second law, but I think it's still important enough to be stated that the net force and the acceleration is always going to be in the same direction, right? And we know that force is just the acceleration multiplied by the mass. So obviously the mass doesn't have a direction. It's not going to change the direction of A but often when I ask students for the direction of or the direction of the net force, they kind of fall apart, right? If I ask you for that, you can also find the direction of the acceleration, and that is going to give you the same answer, okay? So this also does imply if there's net force, there's acceleration, and vice versa. So for example, if an object is sliding up a frictionless inclined plane and slowing down, in what direction is the net force? So that means if it's going up the plane and slowing down, right, the acceleration is going to be down the plane, right? It's opposing the motion. So that means that the net force, even though it's moving up the plane, the net force is going to be down the plane. Okay, so just a note, we will talk about something called static equilibrium. So that is when an object is completely at rest. It might be at rest on a plane or on the ground or in the air. It's just not moving. Okay, static equilibrium, fancy name for not moving. Mechanic equilibrium will be basically the object is moving at a constant speed, right? Constant constant velocity. Yeah, but it's not accelerating. We call that dynamic equilibrium. So there is a difference in terms of the excuse me. In terms of the equations that we use, acceleration is still going to be 0, so it doesn't change the math very much, but it is important to distinguish the two types of equilibrium. So note, and this is very important, that if there's 0 net force, it will almost never, unless you're like hanging out in a vacuum, it will never mean that you are, that there are no forces that are applied to the object. Okay, it basically means that the forces that are acting on the object cancel out, right? So we often see the normal force and the gravitational force. There's an object sitting on the desk, normal force, gravitational force, they end up canceling each other out. Okay, they're equal in magnitude, opposite in direction. So there's a 0 net force, but it doesn't mean that there's 0 force. Okay, so that's very important to note. Okay, so here are the forces that we're going to be dealing with in this class. We have the gravitational force, Fg. Sometimes I'll write it F little g, and that's, either is fine. The spring force, Fsp. Okay, tension is T. Predictably, N will be the lowercase n. Normal force will be the lowercase n. Little f is going to be the frictional force. So with the subscripts, F subscript K is kinetic friction, F subscript S is static friction. And finally, we might have some questions with a thrust force. So that's F thrust, obviously. Obviously, there's other forces that we deal with too, right? A lot of us were asking, about wind resistance or drag, the electric force, magnetic force, that sort of thing. But we're basically going to stick to these forces. So make sure that you note this notation because it's what I'm going to be using in the problem solving. If your notation is slightly different, that's okay, but don't make it too different, right? I shouldn't be guessing what's what. Okay, so just doing a quick run through some of the forces. We start with the normal force, and the definition of the normal force is the when an object is trying to deform another object, the normal force is the resistance force, okay, that keeps the object from being deformed, okay? So if I hit the table, right, the table is not moving, right? The table is, I'm not putting my hand through the table. Obviously, when I put my hand on the table will push up on me with some force, okay, to keep my hand from going through it. This is called the normal force, okay? So it keeps you from just moving through objects. You can think of it like that. So for example, a person lying on a mattress, right? Obviously you sink into the mattress a little bit, but you don't sink absolutely through the mattress and to the ground, right? The mattress pushes up on you, right? Due to the structure of, the fibers and the springs and that. The book on table, pen on book. So obviously the table is exerting a normal force on the book, and the book is exerting a normal force on the pen. Okay, so note that when things are stacked. Also, if some, like, not always is the normal force pointing upwards, right, as we define it. If you are trying to, push your hand against a wall, the normal force is going to act out of the wall, so it's going to oppose, it's basically opposing the applied motion, okay, whether that be gravity or an applied force, or it could even be, friction, anything, okay? So just note that regardless of what direction your surface is, the normal force is going to be perpendicular to that surface. Okay, so 90 degrees to the surface. So that's important when we start talking about inclined planes, which will come. Okay, so the normal force depends on the situation. We really are kind of stuck to solve for it when we know all the other forces. Like, there's not really an explicit equation for the normal force. I mean, we know that there's one that is connected to friction, right, which we'll talk about in a second. But overall, we calculate the force by looking at the motion of the objects and looking at the other forces and kind of deducing it from, whether or not it's in static equilibrium. So when something is just sitting on a table, the normal force Fn, or N, the notation here is a little bit different, it's just going to be equal to the gravitational force, which can be written m times g, right? F equals ma, Fg is equal to m times the gravitational, the acceleration due to gravity. Okay, so there we go. That's the normal force in a nutshell. Let's talk about friction. I guess I should have also had a slide on the gravitational force. I don't think I have that here, but just know Fg is equal to m times g. You probably know that already. Again, it's Newton's second law, just with the acceleration being the acceleration due to gravity. Okay, and of course, you put 9.8, and then, if you need a direction for the force, it's going to be in the same direction as the acceleration. Okay. So the frictional force, we've got two. We've got kinetic friction and we've got static friction. Okay. So obviously it is what it sounds like, right? The kinetic friction is when two objects are moving with respect to each other, right? If I rub my hands together, there's kinetic friction acting between them. Okay. Static friction is when two objects are stationary with respect to each other. And yeah, so there's not moving, it's static, right? So note that we have an equation for the kinetic friction. The kinetic friction is constant. It depends on the coefficient of kinetic friction, which is always going to be a number roughly between 0 and 1. So that just basically tells you how much friction there is on something, or how much friction a surface can have. So something really rough is going to give you something close to 1. Something very smooth is going to be closer to 0. So Fk, the kinetic friction, is equal to mu k times n, which is the normal force. Okay, so that's where the normal force does come into play when calculating the friction there. So we can always use that for kinetic friction. So two objects are moving, we use that equation. Static friction is a little bit different. Okay, we're a little bit more limited with static friction. So basically, static friction will always be exactly what it needs to be. Okay, so say I have my sticky notes and it's on my hand. Okay, so if I start pushing on my sticky notes, well, if I do it lightly enough, it's, my coefficients of frictions are both pretty low, so it really wants to slide. So say I'm pushing on my sticky notes. Okay, they're not moving. Okay, so I have this applied force from my hand, but the reason that it's not moving is friction. Okay, because the friction between the sticky notes and my hand. Okay, so basically the static friction is always going to be exactly what it needs to be. If I push with a force of 1 Newton and the object doesn't move, it's pushing back on me with a force of static friction of 1 Newton. If I push on it with 2 Newtons, it's going to push back on me with a force of 2 newtons, and that's going to be the force of static friction. And so it goes. But let's say I push on it with a force of 4 newtons, and it starts to move. Suddenly, I don't have static friction anymore. I have kinetic. Okay, so the tipping point from where it just starts to move, right? When static friction is at a maximum, it's going to be equal to the coefficient of static friction, which is similar to the coefficient of kinetic, right? It's still just a number between 0 and 1, times the normal force. So that's, if we know this coefficient of static friction and the normal force, we know the maximum amount of static friction that, or basically the maximum amount of force that you need to apply to an object to overcome the static friction, okay, and get it to start moving. Okay, so it's for the static friction, you know, if it's stationary, the value of static friction can be anywhere between 0 and the coefficient of static friction times the normal force. Okay, so, and of course, we're assuming some things, right? Fk is independent of the relative speed of the surface. That's an assumption. It's not exactly true, but it's an assumption that we make. We also assume that Fk and Fs are independent of the area of contact, so the surface area doesn't affect the coefficient of friction. So that's also a bit of a an assumption, right? A simplification, but all good. So I think that yeah, so you apply a force to an object, it stays still, then you get to that maximum force that you apply where it starts to move. You can see that very clearly in this really nice little graph here. We have the static region, so we're applying this applied force to the garbage can in this case. It is not moving, it is not moving, it is not moving until you get to this place where the static friction is maxed out. Okay, you're at your maximum static friction. The surface just can't hold it anymore. So at that point, the object starts to move. Note that the coefficient of static friction is always going to be greater than the coefficient of kinetic friction. Okay, so basically this means, you know, once you get to this maximum static friction, the frictional force drops, right, to mu k times m. So basically this shows you why it's easier to keep something moving than to start something moving. So for example, if you're pushing a box, it might be it might be really hard to get it going, right? Right, because it's really heavy, there's a lot of friction. But if that box were moving, you might have enough energy to keep it moving. Okay, so that's why, for example, if you're pushing something up a ramp, you often get a running start, right? Because you are in motion before taking on that extra curve or the extra uphill, so that you, instead of just like putting the box on the incline and then starting it from rest, you can imagine that being a lot harder. So this is the physical definition of why that which you experience is the case. Okay. Ta-da. Oh, I do have a slide on mass and weight. Oh, how nice of me. Okay, so just a few little definitions, things you know probably already. The mass is, intrinsic to an object. So, a property of an object. It's measured in kilograms. So, like the object will have the same mass anywhere. Weight, on the other hand, is different. Weight is measured in newtons, okay? Weight is a force, and roughly, and we say that the weight is equal to the gravitational pull, okay? So weight is Fg, mass is just the mass, okay? So that's the difference between mass and weight. So if I ask you how much you weigh, you should technically give me a measurement in newtons and not in pounds or kilograms, but I wouldn't ask you that anyway, so whatever. Then we also have the apparent weight, and the apparent weight is the magnitude of the normal force. So typically you might say, all right, if I'm just standing on the ground, my normal force and my gravitational force are going to cancel out. Okay, so well, if they cancel out, then I feel exactly as heavy as I am. All right, my normal force I feel, the amount I feel is equal to the force of gravity that's pulling me down. Um, But however, we could have situations where your apparent weight is not the same as your gravitational force. So for example, when you are moving up in an elevator, and we'll talk about some elevator questions in class because they're very interesting, but when you are moving up in an elevator, your weight is actually offset by the motion of the elevator. All right, so that's why when you start moving, right? As an elevator starts moving upward, at the very beginning, you feel kind of heavy, like, oh, right? That's why, you try jumping as soon as an elevator starts and you like kind of feel like you're going to fall to the ground. You feel very, very heavy. Okay. And when you start slowing down at the top of the elevator, you feel a little bit light. You kind of feel like your stomach is down there somewhere. Okay. That is due to the apparent weight. It's how heavy you feel is actually the normal force. So note that this is also the value that a scale reads. So if you had a scale in an elevator and you started accelerating upward, it's going to read a different amount than if you were just stationary on Earth. Okay, so lots of fun things. Again, we're going to do elevator problems in class. Okay, so the last thing I just wanted to touch on is problem solving for forces. Okay, we'll obviously do lots of examples in our two synchronous classes. You will need to draw a free body diagram, which is super important. Okay, so free body diagram, basically, if you haven't seen one before, it's basically a catalog of all the forces that are acting on an object. I don't have my pen set up, so I would just draw you one. If you haven't seen one before, Google free body diagram and you'll see some examples. So you represent your object by a point, then you draw the different vectors, the different force vectors that are acting on that object. You will also need to draw a coordinate system. Okay, this is not optional. I will deduct marks if there's no coordinate system. I don't care what it is, as long as you're consistent with it, right? You can choose whatever coordinate system you like. You must draw and label the net force. So if the object is moving down the ramp, for example, you have to draw the net force vector being down the ramp. Yeah, unless of course you don't know the net force, and then sometimes you could just write F net is equal to question mark because you don't know. All right, so these things are incredibly important in a forces problem. They're essential for a free body diagram, which is essential to solve a forces problem. So I expect the vectors, I expect the coordinate system, and the net force if you know it. For the rest of the problem, after you have your free body diagram, you should do a little sketch of the problem. Okay, so especially again, if there's not one provided, do a little sketch. Again, usually you start with that because it'll help you draw your free body diagram. Then I want you to use I hat, J hat notation. So this is something where, I hat, J hat is required. So using component vectors, define all of the forces that are present. Okay, so do an inventory. What are the forces? What are the signs on those components based on how you do the coordinate system? So you set that up. Then you will look before that, you'll be splitting up your drawing. If there's 2 dimensions, you'll split it up into X and Y, just like we did in projectile motion. We'll do an inventory. We'll see what we can solve for, okay, based on what we're given in the question. We might use Newton's first and or second law for this. So solve for our unknowns. And then finally, we ask ourselves, is this reasonable? Does it make sense? Do the dimensions work? Do the signs work? That sort of thing. So obviously, I'll show you lots of examples of forces problems once we're in our synchronous class. In the meantime, also look at the examples in the textbook, right? Because those are good examples of solving forces problems. But I'll try to be extra super clear, like I tried to be with kinematics, on what I expect to see in each problem, so that it doesn't feel like a guessing game. So anyway, if you're watching this before the weekend, have a great weekend. If you're watching it during the weekend, continue to have a good weekend. And I will see you in class.